Swayam Prabha. Digital India. Educated India.
Okay, so I'm assuming that pi was a perfect weight. Pi was a maximum weight perfect matching. So what can I write since it's a perfect? Okay, so so I know that the weight of this particular matching pi has to be maximum, right? Since it's a maximum weight perfect matching. So so I can write that VA of pi A summing over all agents. This particular value is the weight of matching pi, right? So I know that since I assume that pi was a maximum weight perfect matching, I know that its weight must be at least the weight induced by the matching sigma, right? Yeah. Remember that I've assumed sigma comma p is NV free. So sigma is some matching. I want to show that given a maximum weight perfect matching, it can be coupled with a price vector to make it a NV free solution. So my goal is to show that pi comma p is again an NV free solution. NV free solution, and I've assumed that pi is max weight perfect matching. Okay. So this particular first step, the first inequality is clear, right? How did I get it? Since pi is the maximum weight perfect matching. So what I'll do is, so this is some jugglery what I'll do. I'll just subtract the p. So this is the p, right? I'll subtract it from both sides. So what I'll get is sigma A minus, I'll subtract this particular price from both sides. So this particular quantity is obviously equal, and I've just subtracted from both sides. Okay. And then what I'll do is I'll just regroup these quantities in a particular way, which is quite intuitive. How should I regroup? So what I'll do is, I know that this particular agent A is getting sigma A room. So I'll just regroup it as V of sigma A minus P sigma A, and then sum it over all agents A. So why this particular quantity is equal to this particular quantity? Why can I regroup in this particular way? Yeah, so since sigma was a matching, here were just price vectors written over here, like price of room 1, 2, 3, 4, 5, 6, and then I just coupled it with the room agent A is getting, right? So these two quantities are exactly equal. I do the very same thing here as well. So I minus P of pi A, right? So these two quantities are exactly equal. I've just regrouped things, and these two values are again exactly equal, and because I've just regrouped. So now, since we had assumed that sigma comma p is NV free, can someone tell me what would be the next argument? Remember, sigma comma p was NV free, and therefore I have this particular inequality that the utility agent A is achieving from room sigma A under the price P sigma A is at least the utility he is achieving from any other room R, right? Remember, this is true since sigma P is NV free. Yeah. So what do I get if I observe this particular thing and try to apply this observation to this particular inequality. Okay. Okay, till now it's all clear, right? Whatever manipulations we have been doing. They may be different, yes. Yes, exactly. Yeah, exactly. So what she's saying is, what I'll do, so this constraint is true for all rooms R, right? I'll just apply, so I'll just apply this particular constraint for agent A on the room pi A. So on the room he is getting under the bijection or under the matching pi, right? So if I do that, I know that VA of sigma A minus P sigma A, this must be at least VA of pi A minus P pi A, because pi A is some room R, right? So this should be true in, because it was true for all R, it should be true in particular for the room pi A, right? And pi A and sigma A can be equal, no worries, but they can be distinct rooms as well. We have equality anyways, right? So here you have, let's say you have these summations here. So this is, let's say, for agent A1, this is for agent A2, A3, let's say we have 3 agents. This is for, again, agent A1, A2 and A3. This is what he is getting under pi matching, and this is what he is getting under sigma matching, right? So I know that just applying NV freeness term by term, I will indeed get this particular equalities. So VA sigma A minus P sigma A must be equal. So I know I have the inequality here, but it would be exactly equal to VA of pi A minus P pi A. This will happen for all agents A. Right? This last step is clear, right? So I've done nothing, but I just observed that since sigma p is NV free, this particular tuple is NV free, I know that I have this particular inequality, and therefore this inequality must prevail here as well. And in particular, this is not an inequality but an equality. Okay, so having this particular equation for all agents, what can I conclude now? So what can I conclude about the allocation pi comma p? So okay, I have this particular equation for all agents, right? So what can I now conclude about the allocation pi comma p? Exactly, it also must be NV free, because just let me write it again. So what I had it, this is exactly the utility he is achieving under another matching, which is a maximum weight perfect matching. This is happening for all agents, right? And I know that this particular quantity was at least VAR minus PR. So, okay, yes. Yeah, okay. So I have this particular equality from last argument, and I know that this holds true since sigma p is NV free, right? So in particular, I know that pi comma p will also form an NV free solution. So in particular, what is happening is, give me any max weight perfect matching of the graph, of the valuation graph GQ, which is, let's say, pi. I can couple it with a price vector such that it will indeed form an envy-free solution, right? So is this part clear? So let me reiterate what in this particular part I'm saying, that give me a random division instance Q, construct the corresponding valuation graph GQ, and then compute a maximum weight perfect matching pi in it. I'm showing that you can always couple it with a price vector such that it will be envy free for the same instance Q. Right. So what is left for completing the proof of the lemma? It is the other way around, which is only if part. Only if part says that, okay, you start with an envy-free solution, let's say sigma comma p, and then you need to show that sigma must be again a max weight perfect matching in the valuation graph GQ. Yeah. So in the other way around, what I need to show that, yeah, let sigma comma p be an envy-free solution. I need to show that sigma is a max weight perfect matching in the corresponding valuation graph GQ. Note that in the previous part we showed that given a perfect matching, maximum weight perfect matching, I can couple it with some price vector to make it an envy-free solution. Right now I'm showing that, okay, give me an envy-free solution, I'll say that this sigma has to be a maximum weight perfect matching and cannot be anything else. It cannot be a suboptimal perfect matching, for instance, yeah. In the previous part, yeah. Yeah, that's what I was, that's what I assumed here, that it does exist. It comes from LP duality, and I wanted to cover it, but I don't have much time. We can talk about it offline, yeah. Or maybe I'll cover it tomorrow. Yeah. So right now, do assume, let's say, envy-free solutions exist under quasi-linear model, and I'm just proving this particular property or characterization of envy-free solutions, where I'm saying that this particular if sigma comma p is an envy-free solution, that sigma has to be a maximum weight perfect matching. It cannot be anything else. And give me a maximum weight perfect matching, I can always find a price vector so that the tuple sigma comma p would be an envy-free solution for the given instance Q. Yeah. Yeah. Okay. Oh, no, okay. So, okay, so the proof of this particular existence is indeed coming. So, okay, here I'm assuming the existence, and then separately I can show the existence via LP duality, and then this particular lemma is just giving a characterization on those sigmas. It's not giving me, it's also giving me how to compute it, because I can compute a maximum weight perfect matching in poly time, and then write an LP, and in that particular LP the envy-free constraints would be a linear constraint given the maximum weight perfect matching. Okay, I'm being vague because, yeah, I've not gone into LP duality at all. Yes. Okay, you just solve the LP, it gives you the solution there. No, okay. So this is a lemma which is telling you about a characterization of these solutions, and an existence can come from LP duality. This is just a characterization of NV-free solutions. We can like take it offline if there's any more confusion, right? Okay. Right now, what I'm trying to prove is a characterization of these sigma comma p tuples, which let's say is NV-free. The sigma must be a maximum weight perfect matching. It cannot be anything else. I know that I've assumed existence right now, but currently I'm just trying to say that, okay, assuming existence, I'm proving this particular, okay, the existence can also come from a combinatorial lemma, which is a variant of Sperner's lemma, and it can also come from, which is called KKM lemma, and existence can be shown from other methods as well, but this is a simpler one, that's it. Yeah, I know it might be a roundabout way of saying whatever, but you can also always assume that the existence is coming from another combinatorial lemma, which is called KKM lemma, and then I'm just trying to prove a characterization for NV-free solutions, and then having these characterizations, I can always compute an NV-free solution as well. Yeah. Okay. Hmm. Correct. Maximum. Hmm. Correct. Okay. Yeah. Okay, to complete the characterization, now I need to show is, give me any NV-free solution, the matching or the bijection sigma must be again a max weight perfect matching. Okay? Yeah. So the proof is via contradiction. For contradiction, assume sigma is, let's say, not a maximum weight perfect matching. For contradictions, suppose not. So which means that there exists some other max weight perfect matching, and let me denote it by, let's say, sigma star. Let's say sigma star is a max weight perfect matching, because if sigma is not, someone else would be. Okay, so I should go to next page. Okay, so I know that I have two things, sigma comma p is given to be NV free, and I've assumed that let's say for contradiction sigma is not a maximum weight perfect matching, and let's say some other matching, let's say sigma star is maximum weight perfect matching in the graph GQ. Okay. So if it's a maximum weight perfect matching, I know that this in particular is true, that the weight of this particular matching sigma star must be greater than the weight of the matching sigma, because sigma is not a perfect matching, right? So this is the weight of the matching sigma star. I know that this has to be strictly greater than the weight of matching sigma, since I've assumed that sigma is not a max weight perfect matching, right? So there's a strict inequality going on here. Yeah. So the proof is almost the same. I again do the trick of subtracting p, or subtracting the summation of PRs from both sides. So this minus summation of R PR is strictly less than the summation of VA sigma star A minus this particular quantity. So I've subtracted this quantity from both sides, strict inequality prevails, and I do the same trick again. I regroup the terms, by which I mean that okay, this goes with this, and again strict inequality, and regrouping the terms, and therefore sigma star A has price P sigma star A, right. Yeah, I've done nothing new till now, and so I need to reach to a contradiction, and the contradiction one can feel that it would be contradiction to the NV freeness of sigma p, right? So can someone complete the argument for me? Like this is, I have this particular inequality, strict inequality going on, and I want to derive a contradiction, right? Because we are doing this proof via contradiction. I have assumed that sigma here is not a max weight perfect matching, and so what is the contradiction here? Exactly, exactly. So since you have strict inequality here, there must exist at least one agent, let's say A only, agent A, such that something like this happens, VA of sigma star A minus P sigma star A. This thing is strictly greater than VA of sigma A minus P sigma A, right? And this contradicts the NV freeness of sigma P solution, right? This particular thing contradicts, which is a contradiction, and in particular contradicting the fact that sigma P was an NV free solution to begin with. It is contradicting the NV freeness for agent A in particular, right? Yeah, here he is getting strictly less utility. Then the utility he is deriving from the room sigma star A. Yeah, and this completes the proof, right? So what we've seen is a characterization of these matchings which can coupled with a price vector to form an NV free solution, right? Yeah. So give me any Renn division instance. Yeah, give me any Renn division instance, and with quasi-linear utilities, I know this characterization of, I know the characterization for NV free solutions, right? Yeah. So sigma comma P is NV free if and only if sigma is a maximum weight perfect matching, is a maximum weight perfect matching in the corresponding valuation graph GQ, right? So this is a characterization, a very, very strong characterization we have under the model of quasi-linear utilities, right? Okay. Yeah. And as he has mentioned that this particular lemma tells you how to compute each and every possible sigma, each and every possible NV free solution, right? You just compute a maximum weight perfect matching in the graph GQ, and then we'll see how via LP duality you can come up with a price vector as well. Yeah. In particular, price vector is the solution of the dual of the LP you consider for maximum weight perfect matching. Yeah. And again, since maximum weight perfect matching can be solved in polytime via linear programs, and the dual of that linear program, if you write, has linear constraints. You can again solve it and you can show it that the dual gives you price vector, and hence in this particular model of Renn division instance, computing NV-free Renn divisions is efficient. Like you can in polytime compute an NV-free solution under the model of quasi-linear utilities. Yeah. Okay. I did want to do the LP duality, but let's see if we get time. Yes, tomorrow we can have a look at it. Yeah. Any questions with this particular model of Renn division? Yeah. Okay, then I'll stop. Yeah.